Okay, so I want to make this, I think we can make this pretty short and sweet. I'd like to give you a chance to get some questions answered and get some work done too. I'm not going to do any big tables. We've done a ton of that. I'll double check to make sure everything's online. All the notes are up there. I thought they were, but I'll check and make sure. Okay, so they're up there for you to prep for that. But this is, I'm just going to pull up some sample problems from the MathXL test. They're shorter, quicker, more conceptual in nature, a lot of them. But let's just pass through these quickly and get you on your way. So determine from the graph whether the function has any absolute extreme values on the closed interval from A to B. What can you tell me? We're looking at absolute maxima and minima. Yes, no, sort of. What's the verdict?
Absolute minimum, but no absolute maximum.
Okay, there's an absolute minimum. Good. Where is it? At A. Okay. Good. So we see at x equals A, but there is no absolute maximum. How come? Okay, because we have an open endpoint there, right? Makes sense. So there is no point the ant could ever stand on and say he's at the highest point on that. Okay, so no. No absolute maximum. Okay, quick review. I put these on just because, we covered this a long time ago. This is the stuff, this is the infinite limit stuff, right? Limits at infinity. But these show up on the table. So I did put these question that's going to be kind of random from, all different possibilities on the test. So what's the verdict here? First one, as x approaches positive infinity, what do we find? Infinity, right? Okay, because we're looking at just the leading terms. If you look at the ratio of the leading terms, the top term is bigger than the bottom term, right? So we know it's going to be infinite. Right away, you know it's going to be infinite, but you got to know what's the sign going to be. Well, if we're approaching positive infinity, my sign of the ratio of the leading terms is going to be positive divided by positive, which gives me positive, right? Now, if I had the same question, say I was doing the same thing, the limit of, call that f of x, as x approaches negative infinity, what would the result have been? We still would have had infinite, but as x approached negative infinity, we would have gotten a positive term divided by a negative term, right? So we would have ended up with negative infinity at that side. Okay? Middle one. 11/16, right? Simple rule. We know that if we have same order top and bottom, we take the ratio of the leading coefficients, and that's going to be my horizontal asymptote on both ends, right? Either plus or minus infinity. Does it matter that that's a minus? No. Minus or plus, the answer is always going to be the same. In that situation, it's the ratio of the leading coefficients, so that could have been either plus or minus there. No difference. Okay, bottom one. Oh, and I forgot to write the limit on that one. So say we're taking, that's f of x, and let's say we're taking the limit of f of x as x approaches negative infinity. What's the answer? Here's the important thing. Bottom is bigger degree than the top. What's the answer? Zero, always. So it doesn't matter. It could be plus or minus, makes no difference. The answer is 0. Bottom grows faster than the top, infinitely faster. So bottom of the fraction explodes, fraction goes to 0. Right? Question?
The slant is when the top one bigger.
Right. So this one, on this one right here, we could calculate a slant asymptote. Now that would be kind of a dirty trick in a way, because that's kind of a tough polynomial to divide out, right? But if we divided that out, we would get a slant asymptote. Yeah. And then because we have to use long division, that wouldn't.
If it's too larger than if the top's too larger than the bottom, it's just nothing.
Then if the top's too larger than the bottom, then it's not a slant asymptote. Then there's no asymptote. There's no linear asymptote. It would be, in that case, it'd be like a parabolic envelope that would, but that's not that useful. That's too complicated. Right, but if it's one order higher than the bottom, when you divide it out, you'll always get a line plus another term that's gonna go away when x goes to infinity every time. Yep. Okay. So how about this one? What if we just, I'm just gonna ask you, here together, we'll just sketch a curve that does all this stuff. So you gotta be able to do this. So let's put, what are the important points on the x-axis then that we need to include? So we got -6, -4, goes all the way up to 2, it looks like, and then 4. Okay, so we could just divide everything up then. I'm just going to make kind of dashed lines here. So we're going to partition the XY plane up into these columns, right? These sections, based on the behaviors of the derivatives. And here's, I guess, if we want to put in, there's the y-axis. Not that we need it. Okay, we can't make this too specific, I mean, we don't have any points to anchor this to the XY plane. We want to get the shape. We're just making a sketch. So how about the first row up here? What's this telling us? When x is less than 6, first derivative is positive and second derivative is positive. So what's the fact that the first derivative is positive? What's that telling us? Positive slope. Okay, it's increasing, right? So it's increasing on that interval. How about the fact that the second derivative is positive? Upward concavity. Okay, so what would that look like then? I got to be going uphill and I got to be concave up. The tangent line has to sit below the curve. So maybe something like that. Does that make sense? The first part? Okay, what changes here? Between -6 and -4, we still have a positive first derivative, but we have a negative second derivative. So it's got to be concave down, right? But it's got to be increasing the whole time. So maybe it's doing something like, well, like that maybe? Does that make sense? Okay. How about, so let's not take that like that. Between -4 and +2, we got negative first derivative and negative second derivative. So I'm gonna do one. Let me fix that so it just looks a little better. Oh, it's close enough. Okay, so what's that going to look like? So it's going to be concave down and decreasing, right? So like that. Now, how about here? Negative first derivative and positive second derivative. Okay, negative slope, bowl shaped up, good. Like that. And then finally, here we get for values greater than 4, both derivatives are negative. Where's it supposed to go?
All the way to 2.
Oh, whoops. Yeah, you're right.
Maybe more like this.
Like that, how about? There we go. And then this guy was, we said was concave up, decreasing, and then finally, when x is greater than 4, what's true? Concave down, negative slope, so it's got to go like that, right? Make sense? So can you tell me where are points of inflection then? At what value specs? So -6, right? Change in concavity. And we can see that, that's where we're making our transition. At 2, we're making a change in concavity, and then at 4, right? So those are all inflection points. And then we only get one extremum, and that was at -4. That's the only place where the first derivative transition sign is right there, right? Okay, questions? Make sense? Okay. So yeah, let's make sense of this. Let's try to come up with a sketch based on this one. Let's do it right on the same one. So the blue curve is the second derivative. The whatever that is, the purple curve is the first derivative. Okay. So we got to identify some points here, some things that are going on. How about if we start with the easier one? What if we start with the first derivative? Can you tell me an important point based on that first derivative? Okay, what's going on? So at 4, something important is happening. What's happening at 4? Slope's changing. Okay, so what does that look like then? It's got to be a horizontal. It's got a 0 value, so it's a horizontal tangent. It's going from positive to negative, so increasing to decreasing. So it's going to have to be a peak, right? So somewhere, let's just put it up here. Right, there's going to be a peak. And we're going to be going from this interval over here where we had positive to negative, so it's a peak. What can you tell me about the second derivative the whole time? Between 0, or between -infinity and 8, the second derivative is what? That's the blue one. Negative. So it's got to be concave down. So it all fits, doesn't it? So everything up through here, it matches that it's got to be like that, right? Does that make sense? Okay, now what's happening? Nothing so profound is happening with the purple one, but the blue function is changing sign. The second derivative is changing from negative to positive. Right there, isn't it? Right? So what's that mean? Got to be an inflection point, right? Changing concavity, so this thing's going to flip around, it's going to start doing that. Now, where do I hit my next extremum? Right here, we got it. So we got transitioning from negative first derivative to positive. So what's that look like? So decreasing to increasing. And we know, I guess, because that's a 0, probably should have drawn a tangent in there, right? So this is going to be another place where we're going to end up getting horizontal tangent and decreasing to increasing. And then we got a positive concavity all the way until we get up to there. So it's just going to look like that. Make sense? Okay, so on this question, it might be worth even just sketching this, because there's going to be some, as I recall on this one, there's going to be some questions about on what intervals is the function increasing and decreasing, right? So there you're just looking at only the purple function, right, where it's positive and negative. It's going to ask maybe some things like, where are any values of x where you have a maximum, local maximum, or relative maximum? Where are any points where you have a relative minimum? So that would be these places here because we're transitioning sign, right, of the first derivative. Where would there be points of inflection where the second derivative is transitioning sign? So it might be worth even just making a little sketch based on the two derivatives. Okay, questions? Yeah.
So did you ever say anything about the
Like at 16?
Yeah.
You know,
You don't know.
yeah, you really can't say much about it because that's where the functions stop. So you could say on the open interval you could say something like this. You could say on the open interval from 8 to 16, the function is concave up, something like that, right? But you can't say what's happening at 16. Okay? All right, so a couple of these. Does the function, mean value theorem. It's been a while since we talked about mean value theorem, right? So let's review that very briefly. It's been a while. So mean value theorem, that's an existence theorem. What are the criteria for the mean value theorem? If this stuff is true, then the mean value theorem guarantees the existence of something. But what, remember? Point C is the second part of it, right? So, right. So, continuous and differentiable on the closed interval from here to here, right? So the two parts of the mean value theorem, part one is f of x is continuous on the closed interval, right? Part two, f is differentiable on the open interval, right? We don't care about the endpoints, just the open interval. If those two things are true, so that's the if, right? If those two things are true, then what's the result? Then what does the mean value theorem tell you about? Well, mean means average.
Then f of a minus f of b divided by a minus b.
Okay, so what you're getting at there is that the slope of the secant line, right? Slope of the secant line connecting points A and B, points at A and B, right?
Yeah.
Is equal to something, right?
Yeah.
So we'll write that part down. So f of b minus f of a, that's just y2 minus y1, right? That's the rise in the function divided by the run in the function is equal to what? This is where, Katie, you were trying to say this a second ago.
Yeah, there's a point C that's on.
Good, perfect. So then there, and this, the words, I don't really care if you remember all the words. It'd be something like, there exists at least one C such that, now the wording, you don't have to get the wording exactly right, but you just get the idea, right? That there's going to be at least one value on the open interval. There's at least one C, and I should say this, on the open interval between A and B, such that the derivative at C is equal to the slope of the secant line. And this is one of those picture theorems, right? It's so much easier to think about in terms of a picture. If we graph, like if here's A, and there's B, and let's say here's our function, all this is really saying then, isn't it? There's A and there's B, here's the points at A and B. All it's saying is that there's going to be some interior value of C such that the slope of the secant line is equal to the slope of the tangent line at that place. So on our picture here, it looks like it'd be, I don't know, right about there, I guess. That look reasonably parallel. So that's going to be our value of C, right? So that average slope is equal to the instantaneous rate of change. The average rate of change equals instantaneous rate of change. Okay? So those are the criteria. Do you remember, and here's another little thing too I just mentioned. It's not like this is that big a deal. But there is, do you remember what the word is? It's not even in our book. But you remember what the word is to describe when a function is continuous on a closed interval and differentiable on the open interval? Think about where would it not be differentiable if it's continuous. Continuous means I can graph the whole thing without picking my pen up off the board, but if it also has to be differentiable, what can it not have? Sharp corners, right? So it's got to be smooth. So we say that these two conditions combined, we just call that smoothness in math. Continuity and differentiability. Just so you've heard it. Okay, so does this function, let's look at this guy up here, does it work? All this is asking about, it doesn't really, I'm not asking you for any values of C, I just want to know, does it satisfy the criteria? Does the mean value theorem apply? So does it apply? Is that function continuous every place on that inclusive interval? Are there any places where that function's undefined? Even or odd root? Which one? It's odd, yeah, the denominator's odd, so no issues there, no x's on the bottom, we're fine, right? It's continuous everywhere. So does the mean value theorem apply? Part one, check. It does. What about part two? Is it differentiable every place on that interval? This is the part that's a little tricky. Okay, what are the kinds of places where derivatives can't exist? They don't exist where a function is discontinuous, but we know it's continuous. They don't exist at sharp corners. Is there any other place where derivatives don't exist? And keeping in mind that derivatives represent slope.
When the function doesn't exist.
Okay, if the function doesn't exist, but this function does exist everywhere, right? So that's not a problem. They don't exist where you get a sharp corner, for reasons we've talked about. But is there any place else? This one doesn't come up as often. What's another place where a slope doesn't exist? And derivatives calculate a slope. Close. What were you going to say? What's a vertical line, right? So when the slope is infinite, right? Okay. So what about this guy? That's hard to see, but if we differentiate it, it's not. What's the derivative of x to the 8/9? The 8/9 x to the minus 1/9, so I'll just put the x to the 1/9 on the bottom, right? Okay, now you can tell. Are there any places where this derivative is undefined?
Oh, yeah.
Where?
Wait. 0.
0, right? The derivative is undefined at 0. And remember, this is the thing that, and I know this was probably, at the time, there was a lot of information coming at you, but I'm going to go back and repeat something I said then, which to me is really an important concept in calculus. The differentiability is determined by continuity of the derivative, right? So you're looking for, when you're looking at the conditions of the mean value theorem, the first step is you want to know, is the function continuous? The next step, where you're asking if it's differentiable, is really equivalent to just saying, is the derivative continuous, right? And so we know that the derivative has a discontinuity at 0, and so therefore it's not differentiable. What is happening in this case at 0? If I take a limit of this derivative, if I take a limit of my derivative as x approaches 0, what am I going to get? I'm going to get 8 on the top. On the bottom, I'm going to get a really small number. I'm just getting infinity, aren't I? Really, technically, I probably have to do like a one-sided limit from the left and from the right. Let's pretend we're approaching from the right, let's say. If I'm approaching from the right, I'm going to get 8 over 0 plus, right? Which is going to give me positive infinity, right? There you go. We're getting an infinite limit, which is a vertical tangent line, is really all that's amounted to, right? So this one it does not apply for the reason that the function is not differentiable on the open interval between the endpoints, between -1 and 3, right? So the answer is, for part 2, no, f prime is not differentiable on that open interval, right? There's an interior point where it's not, where it is not defined. Okay. How about this guy right here? Question? Yep.
This is a stupid question. But
Probably not.
When's x to 8/9? Which is it? Get square rooted or rooted first, or?
Okay, is x to the 8/9? The question is x to the 8/9 the 9th root of 8, or of x to the 8th power, or the 8th root of x to the 1/9, 9th rooted? And you can do it either way, but you gotta be, actually in this you can do it either way. You can do it either way. either way. Because you're always gonna end up with a positive answer either way, right, because the top is even. Okay? That make sense?
But if it then one of them was odd or negative, which one?
So where you, right, so in the spirit of that question, I'll give you another example. What if you had something like this? Here's where you gotta be a little bit careful with that. What if we had the even on the bottom? What if we had something like x to the 3/2? Okay. Try this, then we got Desmos pulled up. Try putting in, let's define f of x as x to the 3/2, and just see what happens. And if you don't have it open, I'll do it up here. So if we plug in something like 4, what should we get back? What's the answer going to be? 8. It'll be 8, isn't it? 8, right? Okay. Now, what's f of negative 4? Undefined, right? What was my point with that? I can't remember what I was trying to say.
Take the square root first and then root it.
Oh, you know what? I didn't even make my own point. I was thinking, sorry. It's not gonna work either way. The answer is it doesn't matter. It doesn't matter. Yeah.
Oh, so you get negative.
Yeah, it doesn't matter.
Oh.
What was I thinking? There was a point, you know how you get something in your mind where there's like, okay, there's a point here I want to make. Oh, I know what it was. For the absolute value. But I don't want to, if we have time at the end, I'll show it to you. Because it's the way you define, here's the difference. And this is all I'm going to tell you for now. And then if I have time, I'll come back to it. What is the difference between the square root of x squared versus the square root of x squared? See, there is a difference there.
Because X can't be negative in the second one.
Because x can't be negative in the second one, but it can in the first one. Right.
You can get a negative.
Right. Say it again.
If you square an imaginary number. Like
You could. You could. You're right. You're right. I mean, you can end up with, but if you're going to, like, if you're going to make graphs of these things in the real plane, what you're going to find is that this is the definition of the absolute value of x, right? For real numbers, this, however, only gives us a partial picture, right? Okay, so it's, anyway, you got to be a little bit careful when you're, just a little bit careful with that. But for all intents and purposes, it doesn't matter which one you do first. They're essentially interchangeable. Okay. All right, so back to this guy. There, no, no. So let's look at one of these. You can be quick. Okay, what about this one? Same deal. Does the mean value theorem apply on the interval from -8 to -6? Let's see. I think I wrote down the interval. That's the interval. Okay, so first of all, is the function continuous? How do we tell? And this is kind of an important concept to make sure you can make these connections. And we talked a bunch about this, but it's been a little while. I wanted to make sure we hit this again briefly. How would you know if it's, well, how would it not be continuous? The only place it would be discontinuous would be at the boundary, right, at -7. How would you know? What's the concept that's going to tell you whether it's continuous or not? Okay, I test a point. So if I test a point, I can do that. F of -7 is what? Where do I plug it in? To the function, yeah, but it's a piecewise function. Which piece does the value -7 fit on? Top or bottom piece? Top piece. So I'd evaluate it in the top piece, and I'd get 49 minus negative 7 is, what is that, 56? Okay, that didn't help me though. How do I know? If it's discontinuous, the ant walking from the left, there's going to be a step there, isn't there? Right? What calculus concept would get at that, would ask that question, to determine if the two parts meet up or if they miss each other and there's a gap, there's a break in the function. Limits, right? You have to take a limit from the left and a limit from the right. If the limits are the same, then the ant's going to smoothly join between the two functions, right? So we'd have to just check, is the limit of f of x as x approaches negative 7 from the left equal to the limit of f of x as x approaches negative 7 from the right. Well, what is the limit from the left? From values smaller than negative 7, well, it's 56, isn't it? Right? We already did the math there. We're just going to evaluate, we're going to take the limit of x squared minus x as x approaches negative 7, and we get 56. What do we get from the right? So that's this part. Now tell me if I'm going too fast. Is that making sense? Right? I didn't write the whole thing down, but the limit of f of x as x approaches negative 7 from the left is the limit of that expression, right? As x approaches negative 7 from the left part doesn't really matter there. I'm just plugging negative 7 in and evaluating directly. It's an easy limit to take. What about the limit from the right? Well, here's the part to the right, the piece to the right of negative 7, right? So the limit of f of x as x approaches negative 7 from the right is going to be 2 times negative 7 squared, so what's that, 98? Minus 3 times negative 7 is plus 21 minus 63. So that gives me 119 minus 63 is 56, isn't it? So the limits do agree. So is it continuous? Yes, it is, right? Now what about, is it differentiable? How do we know if it's differentiable? Right? Differentiable means, we know it's continuous. Differentiable means it can't have any sharp corners. Right? So the slope sensor for the ant has to be the same walking towards the point from the left as it does from the right, correct? Okay. So how am I going to get that? Here's the derivative function. What would I do? Oh, excuse me, there's the function. I kind of gave it away. Take a derivative, right? So we know that f prime of x as a piecewise function. What's the derivative of the top piece? 2x minus 1. Bottom piece?
4x minus 3.
Okay. And then we would just have to see if when we approach from the left and the right, we're getting the same values, right? There's our top piece. There's our bottom piece. At this point, can I say, at this point, can I say that this is when x is greater than or equal to negative 8 and less than or equal to negative 7? Can't say equal, can I? Because I don't know that that the derivative exists at negative 7 yet. That's still, jury's still out on that, right? Down here, this is going to be the value when x is greater than negative 7 and less than or equal to negative 6. But what's happening at x equals negative 7, we don't know yet. We got to take the limits and see. If the limits agree, then yeah, then we can define the value of the derivative there. But if they're different, the derivative doesn't exist at negative 7. So we'd have to do a limit of f prime as x approaches negative 7 from the left and see if that's equal to the limit of f prime as x approaches negative 7 from the right. Those are easy ones to take. As I approach negative 7, what's the limit of the top derivative function? What do you get? Negative 15? Sure. If I evaluate this limit as x approaches negative 7, I get negative 15. How about over here? If I evaluate the other piece of the function, if I evaluate this derivative as x approaches negative 7 from the right, I'm going to get, what, negative 28 minus 3, so negative 31. Those are not equal, right? So what do we got going? Two different slopes. From the left, I'm getting a negative 15. From the right, I'm getting negative 31. And so they meet up at a sharp corner. And so the answer is in here. There's no derivative at x equals negative 7. They don't meet up. So what's the answer to the question then? Does the function satisfy the hypothesis of the mean value theorem on the given interval? No, it does not, because it's not differentiable between negative 8 and negative 6, right? It's not differentiable at negative 7. Make sense? Okay? You good? What's that?
Great.
Okay? Seem pretty enthusiastic. So here's one, I won't even do this one. This is just one where now they're saying it does satisfy the mean value theorem, so find C, right? All we'd have to do here, I don't know, I can do it. You want me to do this one? Okay, so this is the one where now we got to find the values of C, where f prime of C equals the slope of the secant line, f of b minus f of a over b minus a. Well, what's a? Negative 1. What's b? 3. So if I make this calculation, f of b, f of 3 is going to be 2 times 9 is 18, plus 15 is 33, minus 3 is 30. F of negative 1, I'm getting 2 minus 5, minus 3 is, what is that? Minus 4? Did I do that right? No, minus 6, right? All divided by 3 minus negative 1. So 24 over 4. Did I do that right? You guys can check it. Is that right? Looks good? So the slope of the secant line is 6. I just need to find, well, where is the slope of the tangent line 6? Because the mean value theorem would guarantee that. What is f prime of x? What's f prime of x? Okay, and then I just need to find where is f prime of x equal to 6. Solve the equation and find out. So let's subtract 5, get 4x equals 1, divide by 4, and I get x equals 1/4, which is in my interval, right? So there it is. That's all we're doing there. All right, and okay, last couple. So something like this. This is the stuff that's going to, in a way, be probably the most familiar because we've been doing a ton of this. Right? This is just table stuff. Find the intervals on which the function is increasing and decreasing. Use the concavity test to determine the intervals on which the graph of the function is concave up and concave down. Sketch a graph of the function. So this would be best done and most easily done with just probably a table, right? So there's y prime. We got it here at 210.
Yep.
It's going a little longer than I thought. What's y prime? What's y prime? There's the derivative. Okay, x squared, I'm going to get 3x squared over 3 is x squared minus 2x. Okay, and what about y double prime? Minus 2. Okay, so we could, that's easy enough, and I'm just going to be quick. So the function's defined everywhere. Where are gonna be the derivatives of the first derivative? If I set that equal to 0, x squared minus 2x minus 3 equals 0. That's gonna factor into what? X minus 3 times x plus 1 equals 0. What do we get? -1 positive 3. Those are zeros of the first derivative. Zeros of the second derivative. If I set that equal to 0, what do I get? 1. So all I'd have to do here, right, is just evaluate the second derivative. I mean, I could fill up the rest of my table. For values less than 0, I'm going to get a negative, right? For values greater than 0, I'm going to get a positive. So then this is going to be maximum, that's going to be minimum. If I fill in some other points here, I could, I could determine where it's increasing and decreasing based on that table. Okay. Do we want to take? I can take 5 or 10 minutes and wrap this up, and then last problem before the testimony if you want. That'd be good to do. And I'll give you a freebie tomorrow. I'll delete anything you don't like tomorrow. Soon as humanly possible. Within. Give me today. I got a scholarship meeting, and I